Okay, so we're going to be practicing the second derivative test today. Okay, where the first derivative test gives us where our function is increasing, decreasing, and our critical points. The second derivative tells us where our original function is concave up, concave down, and our points of inflection are. Okay, or possible points of inflection. So the second derivative test is just like the first derivative test, except we use the second derivative. So what we're going to do first here, it says determine the open intervals in which the graph is concave up or concave down. Okay, so concavity comes from the second derivative. So first you need to find the first derivative. So the first derivative is going to be 6x minus 3x squared. So take the first derivative. Now we take the second derivative. The second derivative, which is 6x minus 6x. Okay, so that's the second derivative. Just like in a first derivative test, the first thing we're going to do is we're going to set the second derivative equal to 0 and find my zeros. So when I set this equal to 0, I get 6 equals 6x and x equals 1. So x equals 1 is my 0 of my second derivative and therefore a possible point of inflection. So now we're going to do our second derivative test. So again, we put 1, that is my 0. Now we're going to test my second derivative. So I'm going to plug in points on left and right of 1. Like on this side, I'm going to pick 0. And I'm going to test my second derivative. So when I plug in, I take g prime of 0, I get 6. So here, my second derivative is positive. At g prime of 2, plug in 2, so 2 times 6 is 12, and 6 minus 12 is negative 6. So over here is negative. So basically, this is telling me my concavity. So on the left side of 1, this is concave up, which looks like this. This is concave up. On the other side, it is concave down because it's negative. It looks like this. So the cup is down. Okay, so when it's negative, the cup is down. When it's positive, your cup or concavity is up, like that. So my intervals, where it is concave up, is from negative infinity all the way to 1. And it's concave down from 1 to infinity. Okay? So it's just like the first derivative test, except we're using the second derivative, and it just tells us different stuff about our original function. Okay? So here, determine the points of inflection and find the open intervals where the graph is concave up and down. So it's just like the last problem. This time, we got to find or determine if there are points of inflection. Okay? So again, we start off by finding the second derivative. F prime of x is our first derivative. We get 4x cubed minus 12x squared. Then we go straight to finding our second derivative, and we get 12x squared minus 24x. So now we have our second derivative. We set it equal to 0. We take out 12x. We're left with here with x minus 2. So our possible points of inflection are 0 and 2. So here we go, second derivative test. So just like our first derivative test, we're putting 0 is a 0 and 2 is a 0. We're going to test our second derivative. So we plug in negative 1. I'm going to use this one. When I plug in negative 1 to my first factor, I get negative. Second is negative. Negative times negative, it's positive here. Plug in 1. When I plug it in my first, I get positive. When I plug it in my second, I get negative. So concavity is negative there. Plug in 3, I get positive. So that means that these are points of inflection because here I'm up. My second derivative is positive, so I'm concave up. Here I'm concave down. Here I'm concave up. Just like in a first derivative test, if this was positive to positive, it would not be a critical point. It wouldn't be a maximum or minimum. If this was positive and this was positive, then this would not be a point of inflection. But because it changes from positive to negative, and this one changes from negative to positive, they are both points of inflection. And my concavity, I'm concave up from negative infinity to 0, and from 2 to infinity. I'm concave down in between 0 and 2, and that's it. Okay? So yes, these are both points of inflection, and I just POI, that's what I call them. So both of them are points of inflection. Why are they points of inflection? Because our concavity goes from positive to negative or negative to positive. So it's just like a first derivative test. Okay. Now the last one, use the following function, find the relative extrema using the second derivative test. Okay. So I'm going to find relative extrema. Relative extrema come from the critical points. So first I've got to find my critical points. So f prime of x. So that's negative 15x to the fourth plus 15x squared. So remember, critical points come from the first derivative. Okay, so set this equal to 0. I take out 15x squared. So when I take that out, I'm left with x squared here. And here I'm going to be left with negative 1. So my zeros are x equals 0 and x equals plus or minus 1. Okay, so those are my critical points. Now, I'm not going to do a first derivative test. I'm going to use my second derivative to let me know. So I need to take the second derivative. So we take the second derivative here. Okay, so 4 times 15, that's negative 60 x cubed plus 30x. Okay, and again, we're still going to now set this equal to 0. So we find our zeros, so we're going to factor. So we're going to take out negative 30x. When we take out negative 30x here, we're left with 2x squared. And here, when we take out negative 30, we're left with negative 1 equals 0. So our zeros of our second derivative are 0. And when you set this equal to 0, you're going to get x equals plus or minus the square root of 1/2. Okay, so now what we're going to do is we're going to use our second derivative. We're going to test it. Okay, so again, we're going to put 0. We're going to put negative square root of 1/2. That's a 0. And positive square root of 1/2. That's a 0. So we're going to test it now. So the square root of 1/2. So if you remember from your trig, okay, the square root of 1/2 is basically the square root of 1/2 is basically 0.707. Okay, so it's less than 1. Okay, it's basically the square root of 2, which is 1.414 divided by 2, which is 0.707. So when I go to pick my numbers, right here, I can pick just negative 1, because that's bigger than the square root of 1/2. So plug in negative 1 into your second derivative to test it. So you can plug it into the factored form, or you can plug it into the original form. If you plug it into the original form, you're going to get positive 60 minus 30, which is going to be positive here. Okay. Then you're going to plug in, say, negative 1/2 here. Plug in negative 1/2 here, you're going to get, I'm going to use the factored form, so that's going to be positive here. And then when you plug in 1/2, you get 1/4. Positive 1/4 times 2, which is 1/2, minus 1, which is negative. So this is going to be negative. Then you're going to plug in 1/2. Again, I'm going to use the factored form. So you plug in here, you get negative 15 times, and you plug in 1/2 here, you're still going to get 1/4 times 2, which is 1/2, minus 1, which is negative 1/2. So negative 15 times negative 1/2, which is a positive here. And then plug in positive 1, or you can put in 2, or whatever you want to put in there. But you're going to get 2 minus 1 on the inside and negative on the outside, so this is negative. Okay, well, now how is this going to help us with our critical points? So we go back up here to our critical point, f of 0. When we plug in 0 into our original function, we get 0. Okay, well, let's look here. 0 is a point of inflection. So this is neither, because there is no concavity there. When I look at 1, now you can see why I plugged in 1 over here. Since my concavity is negative here, that means I am concave down. If I'm concave down, then here at 1, this has to be a relative maximum, because there's a maximum or relative point here, critical point, and it's concave down. That means it has to be a relative maximum. And you plug 1 into your original one, and right here you get negative 3 plus 5, which is 2. Then you plug in negative 1. When you plug in negative 1, you're going to get positive 3 minus 5, which is negative 2. But when we look here, since this is positive, that means we're concave up, which means this has to be a relative minimum. Because if the concavity looks like this and there's a critical point there, that means that that critical point's at the bottom of that cup, which makes it a relative minimum. So sometimes doing a second derivative test gives you a faster way of doing it than doing a first derivative test. It just depends on the function. But it basically will tell me the same thing. If I had done a first derivative test, I would have had to test basically the same amount of points, but you would have seen at 0 on one side, it would have been decreasing to decreasing, it would have been negative, negative. Okay, but so sometimes it's easier just to use the second derivative test. And if you see a 0, and that's part of the thing, we saw a 0 in our first derivative and a 0 in our second derivative, that's basically telling you that that critical point is neither a maximum or minimum. That is what we call a saddle point. And if you looked at this function, basically the function would look something like this. Go like that, then it comes like this, and then goes like this, and then down like that. It's a 5th power polynomial, right? But since we know that that middle part is neither, it's got to look like this. It goes up like this. So that's my concave like that. Then it goes like this. Then it goes like this. And then it comes back down. So this is your critical point here. This is your neither. And this is your maximum. It looks something like that. Okay. That's your second derivative test.